All right, everyone, welcome. We are going to do a rapid-fire, exam-focused revision of one of the most important chapters in all of chemistry, alcohols, phenols, and ethers.
So let's just jump right in, shall we? We're going to break down absolutely everything you need to know, from the very basic structures all the way to the most crucial high-stakes reactions for your exams. So here's our game plan. We'll start with the basics, then we'll dive deep into alcohols, phenols, and ethers one by one. And we'll finish up with some key comparisons that are, total gold for your exams. Let's get to it. Okay, first things first. We've got to build a solid foundation by really understanding how we classify and name these compounds. Trust me, if you get this right, everything that comes next gets a whole lot easier.
So what's the one crucial difference between an alcohol and a phenol? It's all about where that OH group is attached. For alcohols, it's on a chubby sp3 hybridized carbon. For phenols, it's directly on a flat sp2 carbon in a benzene ring. This one tiny difference, honestly, it changes everything. Now, one of the simplest ways we classify them is just by counting the OH groups. Got one? It's monohydric. Got two? Dihydric. Three? Trihydric. You get the idea. It's simple, but it's fundamental.
Naming. This is where a lot of people get tripped up, right? You've got the common names and the official IUPAC names. So something like tert-butyl alcohol becomes 2-methylpropan 2-ol. You really need to be comfortable switching between both of these systems for your exams.
All right, with the basics down, let's get into the really meaty stuff. We're going to do a deep dive into how you make alcohols and what kind of reactions they do. This section is just packed with high-yield topics.
Okay, lean in for this next one, because this is a biggie. The Grignard reagent is like a magic wand for chemists. It's an incredibly versatile way to make all three types of alcohols: primary, secondary, and tertiary. Examiners absolutely love this one.
And the beautiful thing about this reaction, it's like a recipe. You choose your starting carbonyl, and you know exactly what kind of alcohol you're going to get. You want a primary alcohol? Use formaldehyde. Any other aldehyde will give you a secondary one. And a ketone? Bam! That gets you a tertiary alcohol. It's so predictable and so powerful. Whoa, just look at these numbers. We've got 3 compounds with almost the same molecular weight, but look at the boiling point of the alcohol. It's way higher than the alkane or the ether. That's a huge jump, right? So what gives? Why is it so high?
And here's the secret sauce: hydrogen bonding. It's like these alcohol molecules are holding hands, and they're holding on tight. This creates a really strong intermolecular force, this sort of molecular glue that you just don't see in ethers or alkanes. You need a ton more energy and a much higher temperature to break those bonds and get the liquid to boil.
Okay, let's talk key reactions. Now, for oxidation, you have to remember this critical difference. It's all about control. If you want to take a primary alcohol and stop at the aldehyde, you need a gentle, mild oxidizing agent like PCC. If you use the strong stuff, like potassium permanganate, it's going to blow right past the aldehyde and go all the way to a carboxylic acid. Right, let's switch gears and talk about phenol. Think of it as alcohol's cooler, more sophisticated aromatic cousin. That benzene ring changes the entire personality of the molecule. When we talk about making phenol on a massive scale, the way it's really done in industry, one process stands out above all the rest: the cumene process. It's not just effective, it's also really elegant. So how does it work? Well, you start with this stuff called cumene. You hit it with some air, literally just air, to oxidize it. Then a little acid rearranges the whole thing, and boom, you get your phenol and you get acetone, which is another super useful chemical. A very clever and efficient process. Okay, if there is one question you can bet on seeing, it's this one. Why are phenols so much more acidic than alcohols? The answer, in one word, is stability. When phenol loses a proton, it forms the phenoxide ion. And that ion is super happy because it can spread that negative charge all around the benzene ring. That's resonance at work. The alkoxide ion from an alcohol can't do that, so it's much less stable. That OH group on phenol, it's like a giant welcome sign for incoming electrophiles. It supercharges the ring, making it really reactive. But, and this is a big but, you have to watch your conditions very carefully. Dilute nitric acid gives you a mix. Concentrated nitric acid gives you the explosive picric acid. Same with bromine. The solvent completely changes the outcome. And now for the final piece of our puzzle: ethers. Now, they might seem a little sleepy compared to alcohols and phenols, but don't underestimate them. They've got some very important and kind of tricky chemistry of their own.
When you think, how do I make an ether, your brain should immediately scream Williamson synthesis. Seriously, just burn that name into your memory. It's an SN2 reaction, and it's your #1 go-to tool for making pretty much any ether you want. Now, this part is super important and can be a little tricky. When you try to break an ether with a strong acid like HI, the whole game changes based on what kind of alkyl groups are attached. If they're small and uncrowded, it's a straightforward SN2 attack on the smaller group. But if one of those groups is a bulky tertiary group that can form a nice stable carbocation, the whole mechanism flips to SN1. It's all about finding the most stable pathway.
Okay, we've covered a ton of ground, so let's wrap it all up with the ultimate cheat sheet. This is the kind of slide you'll want to review just for a minute right before you walk into that exam hall. Just look at this, side by side. Acidity, phenols win, hands down. The ferric chloride test only works for phenols. Reactivity and electrophilic substitution, totally different worlds. This is your high-yield summary, right here. Take a mental snapshot of this.
So after all that, what's the one thing that really clicked for you? Maybe it was the versatility of the Grignard reaction, or the simple logic behind phenol's acidity. Whatever it is, hold on to that idea. Thinking about it now will really help lock it in. You've got this. All the very best with your preparation.